Okay, so let's start. Welcome everybody to this problem solving session. It's our week 4, and you have learned the stability stuff in the last week, and we will be solving problems on the same topic today. So, in particular, we'll be covering the stability, like what is stability, how to check stability, whether a system is stable or not. And second thing is we will check a very, very important concept, that is Routh-Howitz stability criteria. So before we move on, I'll just quickly revise the important concepts that you have studied in the last week. So stability. So in the meantime, others will also join. So we say, so there is this concept of equilibrium point or equilibrium state. And this equilibrium point is the resting position of a system. Correct? So this equilibrium point is the resting position of a system. For example, if you take the example of a pendulum, and the pendulum, when that is at rest, so this is that state. So this is called the equilibrium state of a pendulum. So for example, I give some initial condition to this pendulum, right? Let's assume that initial condition is theta. Now what will happen? This pendulum will oscillate, right? It will go here, then come back, then here, right? But we know there is this friction which eventually will bring this pendulum to rest, right? So we perturbed this pendulum initially by angle theta, and with time, this pendulum came back to its original position, which we called as equilibrium point. So then we can say it is a stable system. So a stable system is a system to which, if we give an initial condition, or in other words, if we perturb that system from its equilibrium point, as time tends to infinity or as time goes on, that system will regain.
Excuse me,
Uh,
sir.
yes.
Yeah, your presentation was not visible. Now it is visible.
Okay, yeah, thank you. So, yeah. So I was saying that an equilibrium point or a system is said to be stable if we give an initial condition or if we perturb that system, but that system will again eventually come back to the original position or original equilibrium point or resting position. So then we call that system to be a stable system. So in this case, let's assume there is no friction. So if there is no friction, then this pendulum, if I give it initial condition theta, it will keep on oscillating, right? Because it will never stop because there is no friction. So in that case, we will say that our pendulum is oscillating between the equilibrium point, right? So then that's not stable. That's neither stable nor unstable. In that case, we say it's at the verge of instability or it's at the verge of stability. In that case, we call the system to be marginally stable. So you have something called stable system and something called as marginal stable systems. Marginal stable, right? And in other cases, if we give some initial condition and system doesn't return to its equilibrium point or the response of it keeps on increasing with time, then the system is unstable. You have learned this in your lectures. So you have a stable system, you have an unstable system, or you have a marginally stable system. Now, how to characterize? In control systems, you're given a system, how you will characterize whether a system is stable or unstable or marginally stable. So as of now, only studied you have only studied transfer function approach. So we will take that approach and say how we can say based on transfer function, how we can say whether a system or whether a transfer function is stable or not. As you will progress through this course, you will learn state space method. So this transfer function is conventional. This was the earlier method. Now we have modern tools. We have state space analysis. In that way, we can uh, easily say whether a system is stable or not by looking at the eigenvalues of a matrix, for example. So you'll learn that. That's around in week 12 or so. But as of now, we only know transfer function. So we will judge the stability or instability or marginal stability of a system based on that transfer function, right? So how do we characterize whether a system is stable or not? We look at the poles of the transfer function or the poles of the characteristic equation of the transfer function. For example, in the last week, we studied that the closed loop transfer function of a control system is given by GS divided by 1 plus GS HS, where this HS was the feedback. So this is the closed loop transfer function, and the denominator of this 1 plus GS HS, it is called characteristic equation. So we have this transfer function. We basically check the roots of this characteristic equation, which are the poles of the system. And based on the location of these poles, we decide whether a system is stable or unstable or marginally stable, right? For example, if the poles are on the, so this pole, this is an S domain, we have sigma j omega. So if my pole, this is called RHP, right half plane. This is called left half plane. This is the imaginary axis. So if my poles are on the left half plane, if all the poles are in the left half plane, then I called the system to be stable. Right? So if all the poles of this characteristic equation, they are on in the left half plane, then I say the system is stable. If any one of the poles, or if you have a single pole or like multiple poles in RHP, so then we say if we have poles or a single pole in RHP, even if you have some other poles in the LHP, doesn't matter. Even if you have a single pole in RHP, your system is unstable. Your system is unstable. We have studied how we can now judge how when a system can be stable, when a system can be unstable. But now if we have poles on j omega axis, if we have poles on j omega axis and the poles are simple, they are not repeated, then the system is called as marginally stable system. For example, if I have my pole here and here, since they are complex, they will occur in pairs. For example, I have poles here, so they are not, they are simple poles, so they are not repeated. So in this case, the system is marginally stable. But if I have a scenario where I have repeated poles like this. I have repeated poles on the imaginary axis, then my system is. So if I have repeated poles, at j omega axis, my system is unstable. It's very important. Normally we ignore this point, but yeah, as we will be solving problems, whenever you will have repeated poles on the imaginary axis, my system becomes unstable. So we have stability, instability, marginally stable, And yeah, I forgot to mention this thing. Whenever I'm saying my poles are in the left half plane, my system is stable. Even if my poles are complex or real, doesn't matter. If they are in the left half plane, they are stable, right? So um, now moving forwards. So, for example, you're given a transfer function, you are given a characteristic equation, or you are given a transfer function T of S, 1 divided by S plus 2 into S plus 1 into, yeah, that's it. So if this is the transfer function that is given, so yeah, if this transfer function is given, you can easily say, and I'm saying this is a closed loop transfer function, then this is the characteristic equation. You can easily say my pole is at s equal to -2 and s equal to -1. Then easily you can say my system is stable, right? But sometimes what happens, you have this characteristic equation of order more than three. Like even if you have order three, you will be able to solve that, find the roots of this characteristic equation, and judge whether my system is stable or not. But sometimes what happens, it's very difficult to solve this characteristic equation because you will be having uh, this characteristic equation of fifth order or sixth order. In that case, how you will check whether my system is stable or not? There we use this Routh-Howitz stability criteria, right? So there comes this Routh-Howitz stability criteria comes handy. It's very easy and very important as well. So we will understand. So this with the help of an example, I'll explain this with the help of an example that then it will be more clear. So for example, if we have a question, we are given a closed loop transfer function as s plus 2 divided by s4 plus 8s cube plus 18s square plus 16s plus 8. Right? So we're given this closed loop transfer function, and we have to comment on the stability, comment on the stability of the system. So we're given this system. It's not easy to solve this fourth order equation. It is very like it's time taking, and so we solve this with the help of Routh-Howitz criteria. So what we do, we take characteristic equation. So we know this is an closed loop transfer function. So this denominator is the characteristic equation. So I'll write characteristic equation as S4 plus 8s cube plus 18s square, 16s plus 8. Now, what's the next step? We list down all these powers of s in decreasing order. For example, I write S4, then I write S3, then I write S2, then I write S1, and then I write S0. Correct? So this is my first step. I write all these powers of s in decreasing order. So for example, tomorrow, if you have a characteristic equation of sixth order, so you'll write S6, S5, S4, and so on. Correct? So next thing is you have to write the coefficients, the even coefficients. For example, you have S4, so all even coefficients you have to list. What is the coefficient of S4? The coefficient of S4 is 1. The coefficient of S4 is 1. What is the coefficient of S square? Even coefficients, I'm saying. S square, it's 18. What is the coefficient of next even coefficient is 8, S0. Correct? Similarly, for S3, you have to write odd coefficients. So I'll write 8. That's the coefficient of S cube. And 16 is the coefficient of S. And since there is nothing here, you can just leave it blank or write 0. For the time being, let's leave it blank. Now, how to populate these other rows? How to populate S square, S1, and S naught, right? So for S square, what we do, we multiply this and divide by it. We say like this. It is S square is 8 into 18 minus 16 into 1 divided by 8. Correct? This was this row. Now what should I write here? This row. It will be, and then divide. So it will be 8 into 8 minus 1 into 0, that is 0, divided by 8. Okay, so if I solve it, I'll get, this is 8 into 18 minus 16 over 8, it will be 16. Similarly, this will be 8. Correct? So now I have to populate this S1, right? So if I rub this, or I'll do it like this. S4, S3, S2, S1, and S0. So we have 1, 18, 8, 1, 18, 8, 8, 16, 8, 16, 16, 8. Right? Now we have to populate S1. So S1 will be this into this into this, and divide by 16. Right? So what it will be? It will be 16 into 16 minus 8 into 8 divided by 16, which is equal to 12. Similarly, so I'll write here as 12. And here then this term, you see, what should be here? Nothing, because 16 into here is 0, 8 into here is 0, right? So nothing will come here. Now we have to populate S0. What will be S0? This 12 into 8, right? And 16 into 0 divided by 12. So directly we can write will be 8, right? So once again, I'll repeat. We have to first list all the powers of S in decreasing order, and then we have to list the even coefficients and odd coefficients. Then from that, we have to populate S square, S1, and S naught, so on. So for S naught, it was here 8, right? So now you have got the route array like this. After you are done making this route array, what's the next step? The next step is to see whether there is any sign change in the first column, right? So this is the first column, C1. We have to look for any sign changes. If there is one sign change or two sign change or number of sign changes, they give us the number of poles in right half S plane, right? So here there is no sign change. So there is no sign change. Since there is no sign change in the first column of route array, therefore it implies no pole in the RHP, right half plane. When there is no pole in the right half plane, then my system is, it implies all poles are on the in the left half, right? Then my system is stable. We can say that the system is stable. So basically, you have to check whether there are any sign changes in the first column of route array. So based on that, if you get any sign change, for example, there is one sign change from positive to negative, then you have one pole in the right half plane. But what is that pole? We don't know. We only know there is one pole. From route array, we cannot characterize it, like which pole, or what's the value of that pole, or where that is exactly. We cannot say that. But yeah, we can say that there is at least one pole on the right half plane, which will make the system to be unstable. For example, now let's do one more question. Now let's do this question. The characteristic equation of a transfer function is given as 2s4 plus s cube plus 3s square plus 5s plus 10. Can you try? Can you try this? It's very easy, right? So you have to check, determine whether the system is stable or not. So what will we do? It's a fourth order system. We'll write S4, S3, S2, S1, and S0. Right? Then we'll write the coefficients. We have 2, 3, and 10. Similarly, we have 1, 5, and 0.
The system is unstable.
Okay. How many sign changes? How many roots are in the right half?
There are two roots in the right half.
Okay. So, okay, help me populate this row. So that others will also understand. So now s square will be 1 into 3 minus 5 into 2 over 1. What it will be? It will be 3 minus 10, that is minus 7. Right? So it will be minus 7 here. Similarly, we have 1 into 10 minus 0 divided by 1. So it will be 10. Now we have to populate S1. It will be minus 7 into 5, that is 30 minus 35 minus 10 divided by 7. So roughly that comes out to be 6.43. Then we have a 0 here, or let's not write it. Then S naught will be 6.43 into 10 divided by 6.43. So it will be 10. Is this clear to everybody, like how to make this Routh array? Because uh, like it's very easy. As we move on, the complexity of the problems will increase. So then it will be very difficult to solve those problems. So it's better to interrupt me here at this point if you have understood or not understood. So here clearly we can see there are two sign changes. One sign change from positive to negative, and here another sign change from negative to positive. So there are two sign changes. So it means there are two poles in the right half plane. It means the system is unstable, right? So two sign changes implies two poles in the RHP implies the system is unstable. Okay, so if you have understood this, then let's solve this question. Consider the following characteristic equation and determine its stability. Characteristic equation is 3s4 plus 10s3 plus 5s square plus 5s plus 2 equal to 0. So this is the characteristic equation, and we have to check whether this system is stable or not. Yes, I want answers for this question. By the time you solve it, I'll write another question.
System is unstable. Two sign changes are there.
Okay, so please everybody also check whether it's unstable or not. If anybody is getting stable, please let me know. Did everybody get that answer? Anyone? Anyone who has confusion in that? So it's unstable, two sign changes, right? So one sign change from S square to S1, that is positive to negative. Similarly, from S1 to S0, from negative to positive. Right? So this is an unstable system. Now come to this question. This is a very interesting question. So for the figure shown, so it's a negative unity feedback system. So we have to, we are given that k is greater than 0. And for this system, we have to find the range of k for which this system is stable, right? So let's try to solve this question. You'll be getting these type of questions in your exams, in your assignment. These are very, very important.
K should be greater
So
than 390.
okay, so is that the only condition that k should be greater than 390 so that the system will be stable?
And it is also greater than 0.
Yes, it's greater than 0 and it should be greater than, so k should lie. You're saying k should be greater than 390?
No, no, no. It is less than 390.
Yeah, less than 390. So it's already given that k should be 0, or we'll also see that it should be greater than 0. So the range of values of k for which the system is stable should be 0 and 390. And let's check it for others. Let's check it. So for the time being, please do not answer questions, you at least, because let's give others chance.
Okay, okay. Thank you, sir.
Okay, yeah. So so this is like, see, in this question, there is no characteristic equation provided. We have to look for characteristic equation, right? So this is a closed loop unity negative feedback system. And you know, the closed loop CLTF for such a system is GS over 1 plus GS HS. And HS is 1 here, so it will be GS over 1 plus GS. This is the closed loop transfer function. Then this 1 plus GS will be the characteristic equation. So it's not given directly. You have to compute it. So don't make any mistake by directly taking the poles of this k divided by s into s plus 3 and s plus 10. So you have to first find the characteristic equation, and that's very important. That's a catch in this question. So what will be CLTF? The CLTF will be GS over 1 plus GS, right? So we need not calculate this. We'll directly calculate 1 plus GS, right? Because we need only characteristic equation. So characteristic equation is 1 plus GS which is equal to 1 plus k divided by s into s plus 3 into s plus 10. Correct? So this characteristic equation upon simplification we'll get as s cube plus 13s square plus 30s plus k equal to 0, right? So this is the characteristic equation that we got. So we will be now uh, checking the stability using Routh-Howitz criteria of this characteristic equation. Okay, so what we'll do, our first task is we'll just write s cube, s square, s1, and s naught. Then we'll write the coefficients. It will be 1 and 30. It will be 13 and k. Correct? Right? So after that, we'll just multiply 13 into 30 is 390 minus k divided by 13. And here it will be 0 because there is no term here. There is no term here, so this term will be 0. Now this S naught term will be this into k minus 13 into 0 divided by this 390 minus k into 13. So it will directly be as k. Correct? So now in order for the system to be stable, there should be no sign change in the first column of Routh array. So it means there is C, there is no sign change, and there should be no sign change here and here. It means all the terms should be positive. So first of all, it means my k should be greater than 0, and it's already given in the question that k is greater than 0. So k should be greater than 0 as so it's already given in the question, so no need. But still, if you can see from the first column, k has to be greater than 0. For the second uh, term, like second condition will come from this term. This 390 minus k divided by 13 should be greater than 0. It implies 390 should be greater than k, or k should be less than 390. So we got the condition. The condition is the condition for the system. So the range of k for which the system is stable is 0 is less than k is less than 390. Right? So I hope you have understood. It's very, very easy. You just have to understand the catches, the tricky points here, which are there in the question. So you'll not be provided directly with a characteristic equation, or there will be some other hints that you'll have to look for, right? So now let's solve another question. Okay, I'll give you this question. The question is a feedback system, a feedback system with characteristic equation S4 plus 20k s cube plus 5s square plus 10s plus 15 is equal to 0 is option A, stable for all values of k, for all k. Option B, stable only for k greater or equal to 0. Option C, stable for infinity is greater than k is greater than 70. And option D is unstable for all values of k. Right? So try solving this question. So you're given a feedback system with characteristic equation. So characteristic equation is given. You have to find whether the system is stable or unstable or like stable with what range of k. So you have to check that. So if anybody solves it, please raise your hand. So I'll also try to solve it. In the meantime, we have fourth order characteristic equations. It is 4s3, s2, s1, and s0. This is 1, 5, and 15. This is 20k and 10. Now, if I solve it, it will be 100k minus 10 over 20k, and it will be 15 here. Similarly, it will be here 100k minus 10 over 20k into 10 minus 300k divided by 100k minus 10 over 20k. So yeah, here it will be 0 and the last term is 15. Right? So if I take this term, this is the most complicated term, so I'll take this. So if I solve it, I'll get minus 600k square plus 100k minus 10 divided by 10k minus 1. So now if we can see, this will always be negative. For any value of k, this will always be negative because we have k square here, and it's this is linear k, this is square k, and it's minus sign. So it will always be negative, this term. So when this term is always negative, what does it mean? Now, can anybody tell me which option is correct? So when it will always be negative, we can at least guarantee that there is one pole in the right half plane. So
Unstable
when,
for all values of k.
yes. So when this term is negative, it means there is at least one pole in the right half plane, and we don't care about the other poles. If we have one pole in the right half plane, we're done. The system is unstable. So no need to check for other things, because even at least if one pole is in the right half, no need to check. We're done. System is unstable. It cannot be marginally or stable. All right. So let's solve one last question from this, and I expect an answer this time. So you have to determine the relationship between k and t so that unity feedback control system, carefully read the question. So that unity feedback control system whose open loop transfer function is given below, whose open loop transfer function given below is stable. What is the open loop transfer function? That is g of s is equal to k divided by s into s plus 10 plus t. Now, yeah, please try to solve this. This is a very, very interesting question. You have to carefully read the question and understand the catch points, the points where you are very like you where you'll be easily doing mistakes. I'll give you a hint. So one thing is it's a unity feedback. So if it is unity feedback, then HS is one. Second thing is there is no, this is only an open loop transfer function. So you yourself have to find the closed loop transfer function. From the closed loop transfer function, you need to find the characteristic equation and then solve that and write and make the Routh array. So my characteristic equation will be, I'll straight away write, it's a unity feedback. So my will be 1 plus GS equal to 0, right? So it will be s cube 10 square plus ts plus k equal to 0. So I have made it relatively simpler for you. So now you should be able to solve it. How do we proceed? S cube, s square, s1, and s0 will be 1, t, 10, and k. So 1, t, 10, and k. Then s1 will be 10t minus k over 10 is 0 here. Similarly, here it will be k. Now we are given in the question that this system is stable. So we have to find the relationship between k and t such that my this system is stable. So it means, what does it mean? It means there should be no sign change. It means all the terms should be positive. So my k has to be greater than 0, first of all. My k has to be greater than 0. And my second term, that is 10t minus k over 10, it also has to be greater than 0. So now can anybody come up with a relationship?
K should be less than 10t.
Okay. And greater than 0.
Yes, yes.
So, so if you solve this, it will be 10t minus k is greater than 0, or k is less than 10t. Also, k is greater than 0. It means the required relationship is k less than, greater than 0, and less than 10t. So I hope uh, this is getting clear. Yeah. Yeah, please unmute yourself and ask Siddhant.
Sir, I do have
Please.
a doubt, sir. How to
Yeah, yeah.
find the characteristic equation, sir?
Okay, okay. Thank you. So, see, let me explain. So, I said that you have to find the poles of characteristic equation, and characteristic equation is the denominator of a closed loop transfer function. So if you are given an open loop transfer function g of s, then we had discussed, or we had derived this in our previous class, that so it's like this. You have a open loop transfer function g of s, and when you close it with feedback hs, this is plus, this is minus, then what do you get? You get, now this is my closed loop system. So the transfer function of this system will be closed loop transfer function. And if you derive it, you will get the closed loop transfer function to be equal to G of S divided by 1 plus G of S into H of S. Is that okay, Siddharth? So this denominator is called as characteristic equation. So this characteristic equation is nothing but the denominator of a closed loop transfer function. Now, coming to this question, it is given in the question that we have a unity feedback, right? So if it is written unity feedback, then you have to understand it's unity negative feedback. Otherwise, if it has to be positive, then they will mention that it is a positive feedback. Otherwise, whenever there is nothing mentioned about the feedback, whether it is positive or not, you have to assume that it is negative feedback, right? So you are given in the question that it is unity feedback. So unity feedback means this HS, it is 1. So when HS is 1, my characteristic equation becomes 1 plus GS. So now this is my characteristic equation, and we have to check the poles of this equation only. I have to do nothing with the closed loop transfer function. I only have to check the poles of this characteristic equation. Is that clear how this comes, Siddhant?
Sir, I need to how to determine the characteristic equation S cube term. I solved that, sir, but I didn't get that equation. Can you help me to get that
Okay,
equation?
okay, okay, okay. For this question, for this particular question, how I get this? Correct.
Yes,
Okay,
sir.
okay, okay, okay. Fine. I'll solve this for you. So this is GS. I said characteristic equation is 1 plus GS. Correct. So I'll write 1 plus K divided by S plus 10 plus T. Now I will do cross multiplication. So it will be this into 1. So it will be the same term. S into S plus 10 plus T, then this into K into 1. So it will be plus K, right? Divided by S into S plus 10 plus T, right? So now actually in the numerator also we have GS, this GS. So it will be in the numerator of my closed loop transfer function. Okay, I'll write it complete. This is making like things like doubtful. So let's write it. Let's make it easier. So I have given S into S plus 10 plus T. So correct, this is my GS. So I'll write closed loop transfer function. Closed loop transfer function is G of S divided by 1 plus G of S, which is equal to K divided by S into S plus 10 plus T divided by 1 plus K divided by S into S plus 10 plus T. Correct? Now I'll cross multiply. What it will be numerator is this S into S plus 10 plus T divided by, so divided by S into S plus 10 plus T plus K divided by S into S plus 10 plus T. Now, if you see this term and this term will get cancelled, what you will get? You will get K divided by S into S plus 10 plus T plus K. right? So this will be your closed loop transfer function. From this closed loop transfer function, the denominator is the characteristic equation, right? You don't have to do anything with this numerator, only the denominator, right? So then if you solve it, it will be s cube plus 10s square plus ts plus k. Now is it clear?
Yes, sir. I clearly understood. Thank you very much, sir.
Yeah, yeah, thank you. So now let's do another question. Now this is a particular case of Routh-Howitz stability criteria that we are discussing through this question. So if you have to check the stability of the system with the characteristic equation as S4 plus S3 plus 2S square plus 2S plus 3 is equal to 0. Can you try and can you let me know what is the problem that we're facing whether in order to solve this question? S4, S3, S2, S and S0. 1, 2, 3, 1, 2, 0. Now, now if we proceed for S square, what we will get 1 into 2 minus 1 into 2. It will be a 0, right? So it will be a 0 here. Then 1 into 3 minus 1 into 0 divided by 1. So this will be 3 here. Is it clear? But now how will we proceed? Because we have to divide by 0 and that will be infinity. What should we do? Right? In such cases, when, yeah, we have to use epsilon. So we have to assume, so in such cases, what we have to do, we have to assume a small number, epsilon, which is slightly greater than 0. It's a positive number, epsilon is greater than 0. So we have to assume a small epsilon now, epsilon instead of this 0 and proceed, right? Where epsilon is greater than 0. And why we are assuming this epsilon to be positive? Because if we assume this to be negative, it means we are ourselves imposing a sign change. Then if we are imposing a sign change, then our system becomes unstable. But we do not know that. So in order for our system to be not affected, or we have to not impact the stability, right? So this epsilon is positive. So then if we proceed, what we will get? We get this S will be 2 epsilon minus 3 divided by epsilon. And here it will be 0. Similarly, S will be 2 epsilon minus 3 divided by epsilon into 3 minus epsilon into 0 divided by this. So it will be 3. I hope this is clear. Now what we have to check. If I take this term, it is 2 epsilon, right, by epsilon minus 3 by epsilon. So we cancelled, it will be minus 3 over epsilon minus 2, sorry, plus 2. Right, so we get not plus 2, actually, if we approximate it, we'll get minus 3 over epsilon, right? So, or leave that, don't approximate. Now, if you put small value of epsilon, you'll always get, like for this small value, you'll always get this the coefficient, the term, this term negative. If you check, even if for small values of epsilon, you'll get this term to be negative. So what does it mean? What does it mean? Can anybody tell me? We know that it's unstable. But can anybody tell me how many poles are in the right?
Two numbers.
Two poles are there in the right.
Yeah, two poles are there because from there are two sign changes from S square to S1 and S1 to S0. So there are two sign changes because this 3 is positive. 3 is positive and epsilon we are already assuming to be positive. So there are two sign changes. So two sign changes, it implies two poles in RHP. It implies unstable system. Now, if you have understood this, can you solve this question?
Can you make this system stable?
Can you make it stable?
This is unstable.
Yeah, so as of now, we're not bothering about that because there is nothing we can fix to make it stable. There is no K or nothing. But yeah, there are other
If
questions.
the epsilon is greater than 3/2,
Okay, so if the epsilon is greater than 3/2 here, but we cannot, like epsilon is slightly positive number.
yes, yes.
It's not K. It's not K.
Okay, okay. Yes, yes, yes.
Actually, epsilon was a 0, but just to make sure our things do not go to infinity, we treat it as a small number. We cannot make it any positive number. Then we can easily make it stable. So then there is no point.
Okay. Thank you.
Yeah. So now, can you solve this question? The question is, determine the stability of a system having the following characteristic equation. S minus 1 into S plus 1 whole square into S plus 2 is equal to 0. So can you tell me whether the system is stable or not? This is the characteristic equation, and you have to check whether the system is stable or not. Yeah, anyone? You have to expand S plus 1. Yeah. Please, somebody was asking something. So I'm asking whether the system is stable or not. You can just unmute yourself because I'm not checking charts.
It is unstable because there are two poles on the imaginary axis, repetitive poles.
Which pole?
S plus 1 whole square.
Oh, are there? Okay. But there is one more thing. If you see S minus 1, if we have S minus 1 as a pole, we can directly say that's in the right half plane.
Yes, it is also correct.
So we don't need to check whether we have poles on the imaginary axis or not, but we definitely have to check for the like as of now we are not bothering about marginal stability. I have not chosen any question about marginal stability as of now. As of now, I'm only worried about stability and instability. So you can easily see if from this characteristic equation, there is one pole, S minus 1, which is in the right half plane. So we can say, oh, this system is unstable because one pole, we no need to check. This is an unstable system. Why? Because we have a pole in S is equal to 1. It's a pole in RHP. Correct? So now this question. Now, yeah. this question, the characteristic equation is given by s plus 1, s plus 2, s square plus 1 is equal to 0. And by the way, you said that there are repeated poles there. Are they repeated or simple poles? S plus 1 is equal to 0. Then what should we get? Anyway, we'll come to that later. First, solve this question.
Real pole. It is not an imaginary. Yes.
Which one? Which question?
S plus 1. Earlier question you were asking. S plus 1 whole square. It S equal
Yeah.
to minus 1.
So were there repeated roots?
No. It will not be.
You
It's
had said
marginally
that.
stable.
You are saying
Marginally
marginally stable, but as of now, I'm not worried about marginally stable. Is it like, are there any sign changes in the routes array? In the route how it's table, is there any sign change? Or in other words, so if I have to ask how many poles are there in the left half, in the right half, and on the imaginary axis? So let's solve it. If we solve it, we'll get S4 plus 3S square, cube plus
Right half only one
3.
pole is there, sir.
Okay, right half one pole.
No. Let me check, sir.
Yeah. So S4, 3S cube plus 3S square plus 2 equals to be 0. I think it's 3S plus 2.
3s plus 2.
Is it? Is this the
Yes.
correct equation which I've written? Okay.
Yes, same equation.
Now S4, S cube, S2, S1. So we can write 1, 3, 2, and 3, and 3. Now what we'll get? 2, and 2, 0, and 2. Right? So in place of this 0, I'll write 1 epsilon. Are there any sign changes?
Yes, sign
Are
change is
there
there.
any? Where is sign change? So epsilon is positive. Epsilon is greater than 0. Are there any sign changes? So this is the complete route array which I have made. There is no sign change. Right. But so the system should be stable. The system should be stable as of now. Whatever information we have, as per our information, the system should be stable. But now, if you see from this uh, uh, characteristic equation, we can see there is one pole at -1, another pole at -2, and S square is -1. It means S is plus minus J. Correct? Correct? So
Yes.
we have a pair of poles on the imaginary axis. So so the poles will be something like this. We have at -1, at -2. Now tell me whether it is unstable or marginally stable.
Marginally stable.
Yes, it's marginally stable because we do not have repeated roots, rather we have simple roots on the imaginary axis. So we have learned that when we have simple roots on the imaginary axis, then uh, the system is marginally stable. So, but from Routh array, we were unable to check whether it's marginally stable or not. We would have only concluded that it is stable because there was no sign change. So note this important point, star. Like whenever you have zero in the first column of a Routh array, whenever you have a zero, so if the coefficient above the zero element, if the coefficient above the zero element, sorry, if the sign of the coefficient above the zero element is same as that of element below it, then or it indicates that there is a pair of imaginary roots. So here, if you can see, this is my zeroth element, and the element preceding it and the element after it, they have the same sign. So whenever that happens, you have a zero element, and you have to be very careful. If there is no sign change, you have to look for the sign of the elements before the zero element and after the zero element. And if there is no sign change, if they are of same sign, then my system, then it indicates then there is a pair of imaginary roots. So you have to solve for those imaginary roots and uh, then conclude whether my system is marginally stable or unstable. We will soon take cases where there comes a row of zero, then we make an auxiliary equation and then solve that auxiliary equation, which gives us the number of roots on the imaginary axis, right? So as of now, for the time being, just remember that if you have a zero element in the Routh array and you have to check, and there are no sign changes, so then you have to check the elements that are before that zero element and after that. If they're of same sign, uh, then there is a pair of imaginary roots. Why there is a pair? Because they are complex, and that's complex. Yes. Now, can you solve this question? Determine the stability of a system having the following characteristic equation: s cube minus 3s plus 2 equal to 0. It's very easy. You can straight away say whether it's stable or not, but I want number of sign changes. They will come from the Roth's table, Roth's array.
Unstable, sir.
Stable,
Unstable, sir.
unstable. How many sign changes?
2.
Great. There are two changes, two sign changes. So, anybody else? Yeah, everybody got the answer. There are two sign changes. There are many tricks to solve these questions, but as of now, I'm not telling you those tricks. For example, this is a third order system. You just simplify it, take something common, you'll directly get whether a system is stable or not. But for the time being, we're only interested in like learning the route, how its stability criteria. That's why we'll focus on that particularly. Now, yeah, let's understand something very important. Sometimes what happens if entire row is 0? So what happens if entire row is 0? So how can you proceed in that situation? Because then as of now, we have only understood when there is 0 in the first column, what happens. But if you have entire row as 0, so how we proceed in that case? Then what do we do? Then auxiliary equation is formed. Then auxiliary, I'll tell you in detail what is this auxiliary equation. And this auxiliary equation AS is formed by making the use of row preceding the row of zeros. Correct? And then after we make this auxiliary equation, we replace the row of zeros by d by ds of a of s. And what does this auxiliary equation indicate? This auxiliary equation indicates the presence of roots on the imaginary axis. One more important thing is the roots of auxiliary equation will always be symmetrical about imaginary axis. For example, if you have a second order auxiliary equation and you get one sign change below the auxiliary equation, it means there is one right half pole. But due to this point, the roots of auxiliary equation will always be symmetrical about imaginary axis. For example, you got one pole at 1, then by this point, the other pole has to be at -1. So they're symmetrical about this imaginary axis, right? And one more important point, number of sign changes below auxiliary equation is equal to number of symmetrical poles. That's what I said, number of symmetrical poles. One last point is imaginary poles. If we have to find the poles on the imaginary axis, they are equal to order of auxiliary equation minus 2 into number of sign changes below it. the low auxiliary equation. It's very simple. Why I'm writing 2 into this? Because I know these poles will be symmetrical. So that's why I'm writing sign changes. If there is one sign change, it means one pole is in the right half plane, then the other pole has to be in the left half. So that's why we have to minus those poles as well in order to find the poles on the imaginary axis. Right? So now let's take a question to understand this. Let's take a question. The question is, we have a characteristic equation s square plus 1, s plus 1, s plus 2, s plus 3. Now, this is the characteristic equation that's given. S square plus 1, s plus 1, s plus 2, and s plus 3. Now, how many poles, this is a fifth order characteristic equation. So we have 5 poles, out of which we have 3 poles in the left half plane, right? And we also know that we have a pair of conjugate roots on the imaginary axis. From this expression, it's easy to visualize. For example, we have s is equal to -1, -2, -3, and plus minus j, right? So we know that we have a pair of poles on the imaginary axis. But now let's try to understand it from Routh-Howitz criteria. So if you simplify it, all be our equation, it will be s5 plus 6s4 plus 6s cube plus 12s square plus 5s plus 6. Now try to solve it and tell me which row is coming as row of zeros. So it will be 4, it will be 4, it will be 6, it will be 6. Now, this will be 0. So this we can tackle in 2 ways. This will be 0 and this will be 6. So right now I told you that when we are encountering a 0 element and there is no sign change, so this is that scenario. We have a 0 element in our first column and there is no sign change. What we have to look? We have to look for the signs of the elements before that 0 element and after that 0 element. If they are of same sign, then that guarantees the existence of the poles on the imaginary axis, right? So here, if we can see, uh, the sign is same. It's positive. Both are positive. It means at least it means there is a pair of poles on the imaginary axis. Then we have to see those poles and how we can see those poles. So in this case, it's directly given. The characteristic equation is given in a simpler form, but sometimes it's not possible that you will be able to factor these terms out in the form of this equation, which I'm giving. It's very easy to look directly. We can find, okay, we have these poles and this is marginally stable directly. But no, if you're only given this equation, then how you can find uh, my whether my system is marginally stable or unstable. You need to find whether my poles are repeated or not, right? So in that case, this point will get will tell you, okay, there exist a pair of imaginary poles, but you do not know whether they are repeated or whether they are simple. So now we will solve it with the help of auxiliary equation. We can say this is the row of zeros, because when there is nothing, it means there is zero. Correct? So I said whenever there is a row of zeros, we have to make an auxiliary equation. And how we make that auxiliary equation? We have to look for the elements of the rows preceding the row of zeros. So we have to look for this s square. So in this case, my auxiliary equation will be 6s square plus 6. Correct? So this is my auxiliary equation. Then how I have to populate this row of zeros? I have to differentiate this das over ds. It will be 12s plus 0. So now this 12s plus 0, this 12s actually, this 12s will be used here. Oh, let's slide. So it will be 12s. Correct? So this is 12s. Then if you again see this 12s into 6 divided by 12s, it will be 6. Right? Done. So there is no sign change. As of now, we can say the system is stable. As of now, we can say this, but because there is no pole on the right half. But now we have to check whether there are any poles on the imaginary axis. I already said whenever we form an auxiliary equation, it indicates there are poles on the imaginary axis. Or in other words, I said earlier as well, you have to check for that element, for the sign of the elements before that zero element. So here in that case, one case is we are making an auxiliary equation. It means there are poles on the imaginary axis. And from the earlier point as well, there are poles on the imaginary axis. Now we have to check where are those poles, right? So they will be given by auxiliary equation. See, so auxiliary equation is 6s square plus 6 equal to 0, or s square is equal to minus 1, or s is equal to plus minus j. Right? So the roots of the auxiliary equation are plus minus j. So we know that those roots which are on the imaginary axis are plus minus j. So they are simple poles. They are not repeated poles. It means my system is marginally stable. My system is marginally stable. Now, based on this, if I modify my characteristic equation as S6 plus 3S5 plus 6S4 plus 12S cube plus 12S square plus 12S plus 8. So again, you will get no sign changes. If you solve it, you will get no sign changes. Please solve it and you will get row of zeros. Then we have to conclude whether our system is marginally stable or unstable. Before that, if I factor this out, it will be s square plus 2 whole square into s plus 1 into s plus 2. So this will obviously not be given. I'm just, for your simplicity, I'm saying, so this is the factored version of this equation. So clearly I can see my roots are, so I have 6 roots in total. One is at -1, other is at -2, and the other 4 are at plus minus j root 2, comma, plus minus j root 2. So what does it mean? It means I have repeated roots. It means my system is marginally stable. So you know this information now. For the time being, you know your system is unstable, not marginally stable. So you know this information that your system is unstable, but now prove it using Routh-Howitz criteria, because you will get no sign change. But since you are getting a row of zeros, it means there exist poles on the imaginary axis, and based on the location of those poles on the imaginary axis, which will be given by characteristic equation, we will be able to check whether my system is marginally stable or unstable. This is actually very important, because if you only learn it, number of sign changes gives me the number of poles in the RHP, then you are bound to make mistakes in these questions, because there will be no sign changes. Okay, let's solve it. So it will be S6, S5, S4, S3, S2, S1, and S0. So I'll get 1, 6, 12, 8, 3, 12, 12, then 2, 8, 8. Now this is row of zeros, 0, like this, 0, 0, 0. Similarly, let's not write this 0. Similarly, then you'll make the auxiliary equation. So now let's make the auxiliary equation. Let's go step by step. For this row of zeros, we have to make auxiliary equation. So auxiliary equation will be 2s4 plus 8s square plus 8. Now differentiate it, d by ds of as, it will be, what was that? 8s cube plus 16s, right? So 8s cube plus 16s. So it will be 8 and it will be 16, correct? So this is this give me the values of rows of zeros. Then again for S2, I'll proceed, I'll get 4 and 8. Then for S1, I'll again get 0. So when I get zeros, what I'll do, I'll again make the auxiliary equation. So auxiliary equation is 4s square plus 8. D by ds of as will be 8s only. So it will be, this will be 8, right? And then finally, this will also be 8. Now, clearly, you can see, are there any sign changes? No, there is no sign change, but there are two rows of zeros, or there exist rows of zeros. It means there are poles on imaginary axis, right? So there's no pole on the right half, in the right half plane, but there are poles on the imaginary axis. But how you will find now? So now there is a question whether it is marginally stable or unstable. So now characteristic equation will come at your rescue, right? So we will see. So see, this characteristic equation is of fourth order, and this characteristic equation is of second order. It means it will have 4 poles, this will have 2 poles. But remember, the poles of this, the roots of this characteristic equation will also be roots of this characteristic equation, right? So you only need to solve for this characteristic equation because it's of fourth order. It already contains the roots of the second order characteristic equation. Correct. So let's try to solve this. Characteristic equation is 2s4 plus 8s square plus 8. Correct. So if we take 2 common throughout, so what we will get? We get s4 plus 4s square plus 4. So this is my characteristic equation. We again have to solve, like we have to find the roots of this. So how can I factor this out? So can I write this as s square plus 2 into s square plus 2? It's very easy. How I did that? Very easy. I write like this: s4 plus 2s square plus 2s square plus 4. Then I take common s square. So I'll directly get this. Correct? So this is what I had written earlier. Right? So from here, when you solve it, you can easily find my S1, 2, 3, and 4. They are all plus minus. Sorry, let's not write it like this. So the roots will be, here the roots will be plus minus j root 2 comma plus minus j root 2. The four roots are repeated and they are on the imaginary axis. It implies my system is unstable. So this is very important. You have to understand this, that no sign change does not guarantee that your system will be stable if there exists a zero element or row of zeros. Right? Now, if you have understood this, can you solve this question? Okay. The first two rows of Routh's table of a third order characteristic equation are s cube, s square, 3, 3, 4, 4. Now, it can be inferred that option A, that the system has one real pole in RHP. Option B, pair of complex conjugate poles in RHP. Option C, pair of real poles symmetrically placed around S is equal to 0, or D, a pair of complex conjugate poles on the imaginary axis. Yeah, can you solve it? You're given S3, S2, you have to find S1 and S0. And based on the options, you have to tell me which option is correct.
Sir, in previous problem, in last row, how did you get, sir?
What happened in the last?
Last problem, how did you get last row, sir?
How did we get last?
Last row 8.
This. Okay, great.
No, not this, not this, sir. Not this. Yeah, 8, 8.
It's not.
Yes.
Yeah, it's not. See, did you are you okay with this? How I got this 8?
No, sir. 8, 8 is 64 by 4.
Yeah, divided by 8. So it is like this: 8 into 8 minus 4 into 0 divided by 8. This 8 you have to divide as well. So this and this will vanish. You'll get 8. Is that okay?
Even that S3 is 4 also like that. 8, 8
Yes,
64.
yes, yes, yes. It's like
64
that.
by 64 by
8
32.
into 8, 64 minus 32 divided by 8. It's 4. It's
Okay.
8 into 8 minus 16 into 2, 32 divided by 8. You have to divide as well.
Okay, sir. Okay, sir.
Yeah. So now, can anybody tell me the answer of this question? Can anyone tell me which option is correct? And after that, yeah. Should I solve it? Anybody? See, this is s cube, this is s square, s1 and s naught. We have 3, 3, 4, 4. What will be s1? 4 3s are 12 minus 4 3s are 12, 0. So it's row of zeros, right? So it's row of zeros, or it's a zero element because it's an s1. You can also replace it with epsilon, and then, okay, for example, if I replace it with epsilon, what happens? Then it will be 4 epsilon minus 4 divided by epsilon. It will be 4. So it will be 4. There are two ways to do it. One way is this, and one way is making the auxiliary equation. So clearly we can say there is no sign change. System is not not unstable, but now since there exists a row of zeros, I said that indicates that there are poles on the imaginary axis. So again, this zero element, the element before it is 4, after it is 4, both are positive. It means there is a pair of poles on the imaginary axis. So as per the options, we can see option D is correct, a pair of complex conjugate poles on the imaginary axis. But if you go by this method, you'll only be able to conclude this thing. But that's okay with the questions, like the question is asking only this much. But if the question is asking whether the system is stable or marginally stable or unstable, then you cannot do like this. Then what you have to do, you have to make the auxiliary equation. And auxiliary equation in this case is that will be 4s squared plus 4. And when you differentiate, it will be 4s. 4 to are 8s. So it will be here, yeah, will be 8s. And then if you solve this auxiliary equation, what you will get? S square is minus 4 over 4. That's coming out to minus 1. So S is plus minus J, right? So this S is plus minus J. It means they're not repeated poles. They are simple poles on the imaginary axis. It means my system is marginally stable. My system is marginally stable. Is that clear? Anybody has any question at this point? Okay, now let's proceed. One more important question. You should be able to solve this. I'm giving you characteristic equation. You have to determine its stability status. It's S6 plus 2S5 plus 8S4 plus 12S cube plus 20S square plus 16S plus 16 equal to 0. Tell me which row is row of zeros. I'm telling you there will be row of zeros. which row is row of zeros, then whether the system is unstable or marginally stable or stable. If I solve it, it will be S6, S5, S4, S3, S2, S1, and S0. There will be 1, 8, 20, and 16. Will be 2, 12, and 16. Or if I take this 2 common from this, you can always do that. If I take 2 common, I'll get 1, 6, and 8. So I can directly write like that. To simplify calculations, I just took 2 common. Okay, now what is S4? S4 is again 2, 12, and 16. I'll just take 2 common. It will be 1, 6, and 8. Now you have similar rows. Obviously, you will get row of zeros. So S3 is 0 and 0. And how do we tackle it? By making auxiliary equation, which is S4, 6s squared plus 8. And its derivative is dA over ds. It is 4s cubed plus 12s. So this will be 4 and this will be 12. My 4 and 12, then as I move forwards, my s square will be, or if I take a 4 common, if I take 4 common from this, what will I get? What will I get? I'm just making it simpler, calculation simpler. 1, 3, and my S2 will be 3, 8. S1 will be 1 over 3, and S0 will be 8. Are there any sign changes? Are there any sign changes? No, there is no sign change. But there is a row of zeros that indicates the poles on the imaginary axis. So the system cannot be stable and it cannot be unstable. So it has to be marginally stable. At least we know that it's marginally stable. But now we have to find out those poles, whether they are repeated or they're simple poles. If they are repeated, then my system will be unstable, right? So how do we find that? We take the help of auxiliary equation. My auxiliary equation is S4 plus 6s squared plus 8. Correct? So it's very easy. It's very easy. How you can break it? You can write it as 4s squared plus 2s squared. Then if you simplify it, you will get s squared plus 4 into s squared plus 2 is equal to 0. So what are the poles? The poles are s is equal to plus minus j root 2 comma s is equal to plus minus j2. Now, can anybody tell me whether the system is stable or marginally stable? At least I expect an answer from you right now. Is it marginally stable or is it unstable?
Unstable.
How?
The two repetitive poles are
No, they are not repeated poles. They are root 2 and other one is 2. So this is marginally stable.
marginally stable. Yes.
Yes, so this is marginally. We have to be very careful because you'll solve this question, you'll come this way, and there it will be a multiple type a multiple type option type questions, you'll solve it correctly, but write the answer wrong, because in answers it will be only written marginally stable, unstable, stable, or none of these. So you'll solve it correctly, but you'll write the wrong answer. So you have to be very, very careful. So this is not repeated roots. So the system is marginally stable. So I hope you'll be able to solve this type of questions. There is one type of questions, one question, which is there in your assignment. That is about sensitivity. Let me check that. We have less time, so quickly I'll first solve the questions on sensitivity, then I'll come back on route array again. So sensitivity of a system, it's a very simple concept. For example, if I am saying my system is more sensitive, it means it reacts to very minute changes, right? For example, we say he's a very sensitive person. What does it mean? Even if somebody says very normal thing to him or her, he or she cries. So it means he's very sensitive. So he gets offended or at very, very small things. So that's how in similar manner we define system sensitivity as well. So normally in transfer functions or in this system representation, when we represent our system with transfer functions, we say our system is sensitive with respect to a parameter, right? So so sensitivity, for example, my sensitivity of a transfer function t with respect to a parameter g is given by uh, dt over dg into g over t. You have read it in detail, but for the time being, just remember this formula. So sensitivity with respect to parameter g of a transfer function t is given by dt over dg into g and g by t, right? Now, let's solve a question. The question is, and these type of questions you have in the assignment as well. A unity feedback control system has the open loop transfer function. So we are given unity feedback and open loop transfer function as A divided by S into S plus A. And we have to find the sensitivity with respect to parameter A, right? So we have to find the sensitivity with respect to parameter A. First of all, we are given only the open loop transfer function. We have to find the closed loop transfer function, right? What is closed loop transfer function? Closed loop transfer function T is G of S divided by 1 plus G of S. Why G of S only? Because it's unity feedback. So H of S is 1. So if you solve it, you will get A over S square plus AS plus A. Right? So this is your closed loop transfer function. Now we have to find the sensitivity of this transfer function with respect to parameter A. So my sensitivity with respect to transfer function A will be, parameter A will be dt over dA into A over t, right? Now differentiate this with respect to A, right? It will be S square plus AS plus A into 1 minus A divided by S square plus AS plus A whole square into A over T. What is T? T is A over S square plus AS plus A. Now, how I have differentiated it, I have used the division rule. For example, if you have U over V and you have to find the difference, you have to differentiate this, how you will get it? U dash V minus V dash U divided by V square. So that's what I have used here. And what we will get After simplifying, we get this A and this A will go, right? And this will go up, and then it will get cancelled with this one and this one. It will go. Similarly, this A and this A will go, and my answer will be S square plus AS over S square plus AS plus A. So this is the uh, sensitivity. This is the value of sensitivity with respect to parameter A, and it's your homework. It's your homework to find the sensitivity of transfer function T with respect to parameter A, because in this closed loop transfer function, there is a parameter as well, the small a. So what will you do? You will differentiate this with respect to small a. Then again, just put in the values, and the answer will be minus AS divided by, do check it, do try it, because you have similar questions in our assignment. Correct. So this is the sensitivity. It's very, very simple. Just you have to apply formulas. Before we end today's session, just one very, very important question, very type of question, because you may get these type of questions in your assignment or maybe in your future exams. So you have to determine the condition of sustained oscillation. So the question is, quickly I'll write, determine the condition of sustained oscillations. Sustained oscillation means there are oscillations. So it means when there are oscillations, my system is marginally stable, right? That's why sustained oscillations. In the following control system, and find the frequency of sustained oscillations. So there will be, so it's, if it's a marginally stable system, it will oscillate with, right, between the equilibrium point, and at what frequency it will oscillate. It will oscillate. Okay, yeah, good. So it will oscillate. We have to find that frequency of oscillation. Correct. So your system is RS plus minus S into S square plus S plus 1 into S plus 4. This is C of S, and it's a unity feedback. It's a unity feedback, right? So we are given this system, and we have been given that you have to find the sustained oscillation, the condition, the when this system will be marginally stable, right? And after that, if it is marginally stable, it will oscillate with some frequency. What's the value of that frequency, right? So now clearly you can see you are given with a open loop transfer function. You have to first close the loop with unity feedback and find the. Yes, that's true. Whatever he is saying, it's correct. But we have to first solve. We have to first find the condition. That will come later on. The frequency will come later on. But first we have to find the condition. So how we'll find it? We are given an open loop transfer function. We'll find the closed loop transfer function. That's just 1 plus g of hs, right? And what that will be? So the characteristic equation will be 1 of g plus gs into hs is 1, so the characteristic equation will be s4. You will just solve it. 5s cube plus 5s square plus 4s plus k equal to 0. Now what we'll do, we'll make route array s4, s3, s2, s1, and s0. It will be 1, 5, and k. There will be 5, 4, and 0. This will be 21 over 5. This will be k. This will be 84 by 5 minus 5k divided by 21/5, right? So then S naught, it will be K. Okay, so for a stable system, what should we have if any book can be recommended? Oh, there are many books. Whatever is recommended in your course, it will be, I think, Ogata. So somebody's asking in the chats. I'm not able to read these chats. It's taking time and yeah. Trigonometric functions and converting to okay, yeah, Ogata, or maybe there is Normanize, but it will take time. You better uh, you just try to concentrate, and it's not difficult. So just go through calmly through everything, and it will be easier. So in any case, so now for the system to be stable, what should we have? We should have every term to be positive. It means we should have k, we should have k greater than 0, and we should have this 84/5 minus 5k divided by 21 by 5. It should also be, this should also be greater than 0, and this gives me 84/5 is greater than 5k. It means my k is less than 84/25. Right? So what is my condition? So my condition for stability is, for stability, my condition is 0 is less than k is less than 84/25. Correct? So this is the condition. This, I told you to find the condition. Now, then the question is saying determine the condition of sustained oscillation. So I said when they are saying sustained oscillation, it means my system is becoming marginally stable. So when you put this k should be less than 84/25, then my system is stable. So if I put my k equal to 84/25, right? So if I put my 4 as 84/25, then I can see this becomes 0. This becomes 0. Why? Because 84/5 minus 5 into 84/25, 5 or 5 cancels. This will vanish. It will become 0. Right? So if I put my k as 84/25, then my S1 row becomes 0. It means now there is a presence of roots on the imaginary axis. That is, my system is becoming marginally stable, right? And again, you can check the sign. The sign before the 0 element and after the 0 element both are positive. Then there's a pair of imaginary roots on imaginary axis, right? Now how to proceed? Now we have to find the auxiliary equation, correct? So auxiliary equation will be from this row, S square. So auxiliary equation will be 21/5 S square plus 84/25 is equal to 0. And if you solve for this S, you will get plus minus j into 4/5, which is actually, somebody was saying in the beginning. So it like, what is it actually? It is j omega naught, right? And what is omega naught then? Then omega naught is 4/5 radians per second, right? Is this clear? So we have done this type of stuff for the earlier questions as well, but there they were not asking us about the frequency of oscillation. But here they are given us some values, and for these values they're asking us to find the frequency of oscillation as well. Why? Because from the stable system, they want us to make the system unstable by taking a particular value of gain k so that my system becomes marginally stable. Sorry, marginally stable. So when my system becomes marginally stable, it will oscillate around the equilibrium point, and at what frequency, with what frequency it will oscillate, that we found out to be as 4 by 5 radians. So I think with these questions, uh, with we solved many questions, I think, and I think now you should be able to solve all the questions of your assignment. They are very, very easy questions. Some are a bit tricky, but I think I have covered enough content for you to solve. If you have attended this whole session, then I think you should be able to solve the whole assignment. So that's it. Yeah. Thank you so much, Ranjit. So it's my pleasure. So I'm stopping here. If you have any queries, you can reach out, or if you have any questions, do let me know. So I'm just stopping the recording. Thank you. Yeah, thank you.